Then we have already the angular dispersion formula. Now we are trying to derive the formulas about temporal dispersion, okay, from angular dispersion to temporal dispersion. Here, there is a shortcut based on the oversimplified analysis, okay? You have seen this figure before, right? When we introduce angular dispersion, we mentioned that whenever you have angular dispersion, beta vector is a function of omega, okay? And if you have a propagation distance of L, the effective path length is not equal to L, but L times cosine theta. Theta is the included angle between the beta vector and the reference direction. Okay, we have seen this. Now, our picture could be similar to this case, right? We have a grating pair. This is your incident spin hits the first grating at here. If you look at the reference ray, which is red color here, reference ray is here, right? At wavelength lambda 0, okay? And the wavelength or frequency of interest is represented by blue color. And in the case of our grating pair, is represented here, okay? And what is the included angle? Theta. In this picture, it's delta theta, according to our definition, delta theta. So you have the red reference path length, included angle delta theta. So we expect the effective path length at wavelength lambda of interest should be b times cosine delta theta, according to this formula. Okay? It looks good, and if you take this way, you can derive the dispersion formulas easily. Now we know the path length P is equal to B times cosine delta theta, and of course delta theta is a function of wavelength. And if delta theta is small, okay, which is usually true, you can use second order Taylor series approximation for cosine function, which is 1 minus delta theta squared over 2. Okay? Then, at this point, maybe let's think about the sign of derivative of path length. Is it positive or negative? Why is this important? Because we have already known the derivative of path length is related to the sign of your chirp, right? So it will tell us what is the sign of chirp you can create by using a grating pair. Can you create normal dispersion or can you create anomalous dispersion? Depends on this one, right? The sign of first order derivative. Can you quickly examine the sign of first order derivative?
Which M are you using?
M?
M order.
Do you need M here? If you perform derivative for this equation. Okay, I can tell you the final result. M, the sign of M doesn't matter. No matter it's positive or negative, your grating pair will always give you anomalous dispersion. Actually, you have already know the potential answer already, right? Previously, we have shown angular dispersion only introduce anomalous dispersion, no normal dispersion, right? And this is an angular dispersive device. It should follow the same rule. Okay. So what is the sign of derivative? Or an easier way is just try to think about what happens if you, for example, reduce the wavelength. Will the path length be longer or shorter? If you can know that, you know the sign of derivative, right? B is a constant, so it's irrelevant. When you reduce the wavelength, what is delta theta? Bigger or smaller? Then we need to use the formula we derived in the previous page, right? Delta theta is, let me see. Okay, let's check. For example, if we look at equation 11, if you reduce the wavelength, okay, here we need to assume m is positive or negative, but in the end, m doesn't matter. For example, if we assume m is negative, if for a shorter wavelength, this number is smaller, right? This is a constant, so a smaller number corresponds to a smaller theta d, correct? Okay, then in this case, your delta theta has the same sign as theta d, so this is smaller. And if this is smaller, after cosine, you got a bigger number. So shorter wavelengths, longer path length. 是不是有一个地方有问题？倒过来。嗯？前页 ，OK。Let me see.
M 如果是负的话
，Yes.
让它变小，那这一项就减的比较少。
Oh, okay. Sorry. If m is negative, we have smaller theta d, and after cosine we got 比较大的 theta d. Okay. Then we have smaller cosine and a shorter path length. Okay, so that means your path length is shorter for shorter wavelengths. Okay, then the derivative, the sign of derivative should be positive. Okay. This is one way to examine the function of the grating pair. Or actually, if you know the shorter wavelength corresponds to shorter path length, that means it can compress aperture pulse, right? Aperture pulse, initially your blue color, higher frequency components appear later. If it corresponds to a shorter path length, then after the grating pair, it will appear earlier. So that is dispersion compensation. You can get you can compress the aperture pulse. And that means your grating pair introduce anomalous dispersion. Only anomalous dispersion can compress aperture pulse. Right? So this is one example that you can, without deriving the exact formulas, you can estimate what is the function of the grating pair. Okay, but if you actually perform first order derivative, okay, for this relation, you should get something like this. After derivative, this is 0. After derivative, you have minus 2. 2 and 2 cancel with each other. Delta theta times delta theta derivative here. Okay. But we need to perform second order derivative to calculate the quadratic phase coefficient. But we need some approximation. If this is true, which is usually true, if you perform second order derivative, in theory you have to calculate the derivative of delta theta times delta theta prime, so you got delta theta prime squared. But you have an extra term, delta theta times delta theta double prime. But here we assume the magnitude of the extra term is much smaller. So only this term preserved. Then this is equation 13. Okay. Why do we need P double prime? Okay. because in earlier equation 7, it tells us if you try to calculate psi 2, which is the quadratic spectral phase modulation coefficient, this is a fixed constant times p double prime. Okay, p double prime can be calculated by equation 13, but to do that, you need delta theta prime formula, which is shown in equation 12. Okay, so if you combine all of them together, you have this. After reorganization, you got equation 14. Okay, so everything's here. You got a closed form formula. Just substituting the corresponding parameters, you can directly get second order or quadratic spectral phase modulation coefficient. 就是那个相位调变的曲率啊，二阶项就直接用这个公式算出来。Then we can look at the characteristics of equation 14. First, it's always positive. Okay? M squared positive, lambda cubic positive, B is a path length, always positive. And the denominator, you see square, square, square. So everything is positive. Equation 14 must be positive. And it means grating pairs induce anomalous GDD always. It will always create a concave spectral phase modulation curve, meaning the anomalous dispersion. Secondly, psi 2 is proportional to B. Okay, B is the distance of the reference ray between the two gratings, and it's equal to normal distance G over cosine theta D. So it means the GDD is tunable, can be smaller or larger depending on G, the normal distance between the two gratings. So if you tune the two gratings closer, you got smaller anomalous dispersion. Making it bigger, you have greater anomalous dispersion. It's tunable. Okay. You can also calculate cubic spectral phase modulation coefficient by equation 8. But for that purpose, you need not only p double prime, which we have already calculated, you need p triple prime. So more sophisticated calculations are needed. I just skip the intermediate steps, writing down the result, which is equation 15. A lot of constants, but minus psi 2. Okay, psi 2 is calculated in equation 14. So what does this mean? If psi 2 is always positive, psi 3 has a minus psi 2 relation. So it means psi 3 is always negative. Okay? So grating pairs can hardly compensate for second order and third order spectral phase simultaneously, because usually the material dispersion has negative psi 2 and a negative psi 3. The second order coefficient can be compensated, but third order coefficient could be even more serious after you use grating pair, because they share the common sign. Okay? After the grating pair, original positive psi 3 becomes even more positive. So you will have stronger cubic phase modulation. So that is the potential problem of grating pair. So in real applications, if you just use Tracy grating pair as your compressor, you can adjust the grating separation properly. And to some extent, you can almost perfectly compensate for the quadratic spectral phase. But at that point, you have a strong cubic phase. That means in time domain, you have an ugly shape. Okay, oscillating tail. Let me show you one example. Okay, I have a 3C grating pair. The instance angle theta I is assumed 65 degrees. Grating pitch is 2.5 microns. If you look at the spec of grating, it will tell you the grating is 400 grooves per millimeter, corresponding to 2.5 micron pitch. Okay, and supposedly the grating is designed for m equals -1. And assume the normal distance between the two gratings is 20 centimeters, maybe just like this. Okay? And according to equations 14 and 15, you can quickly calculate quadratic spectral phase coefficient is 0.24 picosecond square. Cubic phase coefficient is minus 4.77 times 10 to the minus 4th picosecond cubic, assuming a central wavelength of 1550 nanometers. Okay. But I believe these numbers do not make sense for you. They are just numbers, right? So let me show you simulation curves. Okay, the red dashed curve is the spectral phase modulation created by this 3C grating pair. Almost parabolic, right? Okay. I have to mention that this red curve was not derived by just substituting these two numbers into a third order polynomial, then plot, not like that. I used the instead of the simplified formulas, I use path length calculation, okay? So this curve is more precise, but you can see it's almost parabolic. That means quadratic phase dominates in this case. Higher order phase is relatively weak, okay? Simulation window is, if you look at the upper axis, longest wavelength is 1580 nanometers. Shortest wavelength is 1520 nanometers. The bottom axis is the angular frequency axis. OK， 所以上轴跟下轴都代表颜色啦，只是一个是角频率，一个是波长来画。OK， 那你会得到这样子的一个 spectral phase modulation curve with this simple 3C grating pair. And you can also check the range of phase, okay, from 0 to maybe 60-something radians over this spectral range. So this is a huge phase modulation, right? Many times 2 pi, right? But maybe this is not good enough. So if you calculate the corresponding group delay, okay, represented by the blue solid curve here, because the red one is almost parabolic, so after derivative you got nearly a line, right? 几乎就是一条斜直线, okay. And if you look at the left axis, you can see the blue curve ranges maybe from -6 to +6 picoseconds. This is the group delay created by the grating pair. Okay. Then let me ask one question. If you have a short pulse, the wavelength range is 1520 to 1580 nanometers, the entire range of this simulation. Okay. You can quickly calculate the transform limited pulse duration could be 60 femtoseconds. The question is, after passing through this grating pair, what is the output pulse duration? If you know 60?
Almost
60 what? Femto or pico? Femtosecond, so no change, no significant change. 60 femtosecond in, 60 femtosecond out. Is that what you mean?
Yeah.
Why? Yes.
Because it's already transform limited, so you cannot compress it further.
Yes, I cannot compress. So the answer cannot be smaller than 60 femtoseconds. Should be bigger. But how big? Can you quickly get the number by these figures? By this figure. 1550 here is central wavelength, so 0.
60个 femtosecond 加12个 picosecond.
So it's almost 12 picosecond. Is that what you mean? Because 60 femtosecond is almost nothing compared with 12 picosecond. Okay, right. But how do you get the number? By looking at which curve? Yes, blue curve is more useful in this case. Your longest wavelength takes about positive 6 picosecond to pass through, but your shortest wavelength takes about minus picosecond to pass through. So in the time domain, the separation is about 12 picosecond. So 60 femtosecond in, 12 picosecond out. The stretching ratio is very big, 200, right? So this simple device, just 2 gratings. The grating pitch is very easy to be fabricated nowadays. Separation is quite short, just 20 centimeters. So a very small, a very compact grating pair can stretch your pulse by 200 times. Okay, so this is the one example I want to show you. Good. But as you might have identified, sorry, this is about the challenge about the oversimplified analysis. So far, we got the formulas we need easily, but is it true or there is some problem inside the oversimplified analysis? Okay. Let me briefly review what is the picture we used in deriving this set of formulas. Okay, here, this is the picture we used. Starting with this one, and comparing these two, quickly write down the path length is b times cosine delta theta. But this is risky. This is not the true case, right? What is the true path length under the geometry of grating pair? It's not like this. Stop nowhere, right? How do you justify it stops here? Okay. Correct. So I show you the true picture, okay? If you look at the reference ray, incidence, first grating, second grating, okay? What is the path length of the reference ray between the two gratings? Should be a Z-shaped path, right? From here to here, here, and here. But why just this Z-shaped path? Because before this point and after this point, every colors share the common path. So you do not need to calculate the path length difference. The difference only occurs within this range, right? So what is the total path length for the reference ray? It's shown here. There is a right triangle here, right? This B is the hypotenuse, 斜边. You have two extra passes from here to here and from here to here. But if you project the upper pass onto the bottom axis, actually the summation of the two equals the leg of this right triangle. So the total path length is just the hypotenuse plus the leg of the right triangle, which is B times 1 hypotenuse, B times cosine of theta I plus theta D, so you got the leg length. Okay? How about other colors? For example, we have blue color. The formula is the same, except that you have to change theta D to theta D of lambda, the diffraction angle as a wavelength of interest. In this case, it follows the blue dashed path, also a z-shape. This is the true length, path length. Okay, so it does not rely on the oversimplified picture. Okay, but when you try to calculate the spectral phase modulation function, in addition to this term is natural, right? Omega over c means wave number times path length. The product is phase modulation, you know that. But if you stop here, it's not correct. You have to add an extra correction term, R of omega, which corresponds to the contribution from the grating pitches. And the reason is now different colors may hit different grating pitches, right? For example, the red one hits here, the blue one hits here. They correspond to different grating pitches. And for one neighboring grating pitch, you need a 2 pi phase shift. That is translated to the grating phase. Without this term, you will arrive at a wrong result. But if you take this into account, you can show you still arrive at the same formulas as we used in the oversimplified analysis. So the results are the same, but this process is more official, more correct. The earlier one is easy, but with some problem there. Okay, and you are encouraged to refer to this reference paper to see the discussion about the grating phase physics. Okay, I just give you a very simple description about the origin of the grating phase. For a movement of one pitch, you need a 2 pi phase, grating phase, but it looks kind of strange for you, so you are encouraged to look at this paper for the details. Okay, any question? If no question, maybe we stop here. And next time we will talk about the spatial chirp issue of the grating pair, and maybe the chirp mirror. Okay.